Okay, well now we're ready to write down the energy levels for an electron in a spherical quantum dot and figure out what the optical transition would look like. All right? Hang on for 1 second. I want to show you these results in PowerPoint. Okay, so in the optional video, we found that the energy levels for a particle in an infinite spherical well, particle in a spherical box, if you will, were given by this formula here. The energy depends on two quantum numbers, L and N, and it's given by h bar squared over 2ma squared, where a is the radius of the quantum dot. And then that is all multiplied by z squared, where z sub n L is the position of one of the zeros for the spherical Bessel function j sub L. And the first few zeros are given in this table here. That's a little complicated, but just to illustrate how that works. In the case where L equals 0 for these states, then the zeros just occur at 1 times pi, 2 times pi, 3 times pi, and so on. For the other cases, it's a little harder to find them, but they're all tabulated someplace. In any case, turns out that we're really only interested in the lowest energy state. When electrons get into these quantum dots, they rapidly drop down to the lowest energy states, and those are the most important for us. And for the lowest state, that's n equals 1, L equals 0, the energy is h bar squared pi squared over 2 m star times a squared. Again, a is the radius of the quantum dot. And you know, we could almost have guessed this formula because it looks just like the formula for a particle in a one-dimensional box where we would replace L with A. Okay. Now, what kind of optical transitions can we have in a quantum dot? Well, we can have interband transitions where we go from electron state to a hole state, or vice versa. Suppose that an electron makes a transition from this lowest confined electron state to the highest confined hole state. So that's a relaxation and a photon is emitted. What's the energy of the photon? Oops. Well, it's just given by this formula. HF will be the sum of the band gap energy, e.g., the confinement energy of the electron, and the confinement energy of the hole, here. Where the confinement energies of the electron and the hole are given by the formula we just wrote down. Only in one case we're using effective mass of the electron, in the other case, effective mass of the hole. Okay? So it couldn't be more straightforward. And when we do that, what we find is the following. If I imagine quantum dots made of some material, like cadmium selenide, the energy of the photons emitted in this process will vary with the size of the quantum dot. As the quantum dot gets smaller, as A gets smaller, these confinement energies will get bigger. And so the fluorescence will be shifted to the blue part of the spectrum. And that's exactly what's seen in these materials. And now it's possible to get fluorescent materials like this, where the color of fluorescence varies from red to blue, but the fluorescent object, the quantum dots, they're all made out of the same material. The only reason that the emission color changes is because of this quantum size effect. Okay? Well, that's what I wanted to get to. I think we'll stop here. All right, see you in class.